Hi guys, I'm Fariha.
I'm Bimi.
I'm Kamsi.
We're the senior design students who design and build a perfusion bioreactor. This is our poster for it. So the goal of our experiment was to build a cost-effective perfusion bioreactor that would be available to high school and college students. We built the device to study the effect of shear stress on endothelial cells that is compared to the cardiovascular system on their cytoskeletal remodeling. So it consists of three phases: design, building the prototype, and test and validation. A bioreactor is used heavily in industries and research labs for cell culturing under physical and chemical environment that is controlled. However, it costs thousands of dollars. The needs of our experiment was to show what happened to blood vessels under high blood pressure. So the design requirements included the functional requirements, which was shear stress of 2 Pascal, the media flow rate of 3 milliliter per second, viscosity of 1.3 cp, and media density of 1000 kilogram per meter cube. The physical requirement set was 1 millimeter of depth of flow chamber, and we got the weight of the bioreactor to be 2.186 gram, and volume was 1.792 centimeter cube. The whole system cost only about $1,200, including all the tubing, pump, and everything. We followed good manufacturing and good lab practice, and we used the Navier-Stokes equation as our guiding equation for the design.
So here we have the designs that we came up with. We have the SolidWorks design shown here. We're able to use SolidWorks for the modeling of our device. So figure 2 shows the dimension of the bioreactor. And then we have figure 3 showing the cross-sectional areas of the chamber of the bioreactor. We have figure 4 showing the exploded view of the bioreactor as well. And then we're able to do the computational fluid dynamics, which we use to evaluate the requirements that were given to us for the bioreactor. So at a driving pressure of 1500 pascals, we're able to get a shear stress of 2 pascals. And then the figure 6 shown below shows the oscillating pressure loading, which is similar to the driving frequency to the arc of the endothelial cells as well. And then we're able to fabricate the device at the UTA Arlington Research Institute using the method stereolithography because of the resolution of the bioreactor. And so we fabricated the device using the polymer resin, and then we used the UV laser beam to cure it. And so the figure 7 here shows the base of the bioreactor and the leads of the bioreactor before assembly.
Okay, so for the flow system, it consists of a bioreactor, a peristaltic pump, pressure gauges, flow meter, and the silicone tubes. According to the picture on the bottom, figure 8, it shows that the flow starts from the peristaltic pump and goes all the way to the reservoir. The cell will be cultured inside of the bioreactor, which will be put inside the incubator. After 24 hours, the cytoskeleton structure of the cell is going to be viewed using a phase contrast microscopy to evaluate remodeling. Our expectation for the results is that at a flow rate of 3 milliliters per second, the cytoskeletal structure of the cell will have remodeled at a shear stress of 20 dyne per centimeter squared, as shown in the figure to the right below. Our experiment proves that the fluid mechanical forces can directly influence endothelial cell structure and functions. In conclusion, we were able to design and build a perfusion bioreactor prototype that meets all our design parameters. However, we were unable to evaluate the biological effects of the shear stress on the cultured cell due to the coronavirus pandemic. We would like to acknowledge UTA College of Engineering for the undergraduate experience we got, Dr. Chong, our faculty mentor, for his guidance in this project, Dr. Bervahani for his contributions towards our project, and finally David, who helped us for the fabrication of the device at UTA. Thank you.
Thank you.